A 10.0 liter balloon contains helium gas at a pressure of 655 millimeters mercury. What will be the final pressure if the volume changes to 2.50 liters? Now, the first thing I notice about this problem is we have pairs, and when we have pairs, we're going to have to use a combined gas law equation. I have a pair of pressures. I have a pair of volumes. All right, which means I'm going to have to use our combined gas law equation. Well, that's what we start with. There we go. There's our combined gas law equation. And the way we're going to use it is whatever we don't use, we're going to cover up. And so what are we not using here? Well, it looks like there's no temperature. So this is the equation that we're going to have to use. P1 V1 equals P2 V2. That's our equation that we're going to have to use to do this problem. Now, we're always starting with these pair problems. We're always starting with the combined gas law because it's the easiest thing to do, and the easiest thing to remember is starting with your combined gas law. So there's the equation we're going to have to use. Now, we have to do a little bit of rearranging because what are we looking for? We are looking for the final pressure. And so final pressure would be P2, so I'm going to say it's P1 V1 divided by V2 equals P2. I just divided both sides of the equation by V2 to get our final pressure P2 by itself. Now, the next thing that we want to do is we want to make a table. So let's go ahead and make a table of the variables that we have. So we got a P1, we have a V1, we have a P2, and we have a V2. What's P1? Well, there's pressure 655 millimeters mercury. And what's V1? Well, V1 was 10.0 liters. What's P2? I don't know. And what's V2? Well, V2 changes to V2 is 2.50 liters. Okay, so I pulled everything out of the problem and I've made a table. I have a table of P1, V1, P2, V2. The reason why we use a table for these sort of problems is because it will help you be organized as you're trying to do this. Organization goes a long ways. And so now what? Well, we have the numbers that we pull out of our problem. We have the equation that we're going to use. Now all we have to do is transfer those numbers to the equation and go ahead and write it out and then put it in our calculator. So what do we got here? I got P1. Well, that was 655 millimeters mercury. I've got V1. Well, that was the 10.0 liters over there. Divided by V2. What's V2? V2 is the 2.50 liters. Put those in my calculator. Let's see what we get. And so I put in 655 times 10.0 divided by 2.50, and I get a new pressure of 2,620 millimeters mercury. 2,620 millimeters mercury. Now we should go back through and do significant figures. I have 1, 2, 3 significant figures here. 1, 2, 3. 3 because trailing zeros are not significant unless you have a decimal. And I have 3 significant figures here as well with a trailing zero with a decimal. So our answer should be 3 significant figures. And we look over here, we got 1, 2, 3. That's a trailing zero. We don't have a decimal. So sure enough, our answer is in the correct number of significant figures, which is 3. So our final answer is 2,620 millimeters mercury. A sample of nitrogen, N2, has a volume 50.0 liters at a pressure of 775 millimeters mercury. What is the final volume in liters at 80.0 torr? All right, so we have pairs of variables up there. We have a pair of pressures, and a pair of volumes. So we're going to start with our combined gas law equation. P1, V1, T1, P2, V2 over T2. Let's go ahead and make a small table. And so what do we have up there? We've got a volume and we have a pressure. Let's say we're going to have pressure 1, volume 1, pressure 2, volume 2. What's the initial pressure? Initial pressure is 775 millimeters mercury. And our beginning volume is 50.0 liters. Here they are. We got 50.0 liters and we have 775 millimeters mercury. Let's see, what's our ending pressure? Well, that would be 80.0 torr. And our ending volume, well, we don't know what that is. All right, so I pulled out everything from the word problem. Made myself a table and I pulled them down. Now, there's a problem with what we have here. And the problem is that the units are not consistent. The units are not the same. And so what we're going to have to do is we're going to have to make them the same units. Now, in this problem, we weren't asked for any sort of final pressure or whatever. We were given the pressures. So it doesn't matter which one you pick. You can either change the millimeters mercury to torr or the torr to millimeters mercury. Now, if you recall, torr and millimeters mercury are the same number. It's 760 millimeters mercury. 760 millimeters mercury is equal to 760 torr. All right, that is the case. And so really all we got to do is change, well, you know what, I'm going to change the torr to millimeters mercury. Now, if this had been in atmospheres, we would have had to do the conversion 760 millimeters mercury per atmosphere. We'd have to do the conversion. But in this case, since they're already equal, 760 millimeters mercury is 760 torr, we can just change the units there. Now the units are the same and we can proceed. And so let's see, we're not changing the temperature, so we should cover up the temperature and use this equation right here. P1 V1 equals P2 V2. What are we looking for? We're looking for the second volume, and so we're going to divide both sides by P2 to get V2 by itself. So that's P1 V1 over P2 gives me V2. And now we're ready to go ahead and put in our numbers. We should always wait until the very end to put our numbers in after we've rearranged the equation. And so I put in my numbers that are in my table. And I got P1 is 775 millimeters mercury. I have V1 is 50.0 liters divided by P2, which is 80.0 millimeters mercury. And we put that in my calculator, and what do I get? Let's take a look here. 775 times 50 divided by 80. And we get 484.375 liters, which is our new volume. Now we still need to do significant figures for this, and significant figures would be 3 sig figs here. This is 3, that's 3, so our answer should be 3. And so we go 1, 2, 3. There's our answer with the correct number of significant figures, 484 liters. That's our final answer. A sample of neon has a volume of 2.50 liters at 15 degrees Celsius. What is the final temperature in degrees Celsius if the new volume is 7.50 liters? Now, we are going to be using the combined gas law to get us the appropriate equation that we're going to use. And so, once again, we're going to start with P1 V1 equals P2 V2 T2. And let's go ahead and make a small table of the numbers that we have in the word problem. And so it looks like we're going to be using volume and temperature. We have a pair of volumes, 2.50 liters and 7.50 liters, and we have a pair of temperatures as well. So V2, T2. Let's see, our starting volume is 2.50 liters. Our starting temperature is 15 degrees Celsius. Our ending volume, well, that's 7.50 liters, and our ending temperature, we don't know what that is. We're looking for the final temperature. So our starting volumes are 2.50 liters, and starting temperature is 15 degrees Celsius, and our ending volume is 7.50 liters. Now, anytime that we do a gas law problem, what do the temperature units have to be? They have got to be degrees Kelvin. They have to be in Kelvin. So how do we get Kelvin? We will add 273, and that is 288 Kelvin. The other units are fine. They're both in liters. And now we want to know what the new temperature is going to be. Now, the equation that we're going to use, we're going to cover up whatever that it is that we're not using. We're not using the pressures. So the equation that we're going to use is V1 over T1 equals V2 over T2. This is the equation that we're going to end up using. Now, the easiest way to do this sort of equation here is you can either solve for T2 or you can just use cross multiplication. Most folks are going to prefer to use cross multiplication. So let's go ahead and plug in our numbers that we have. And let's see, I got V1 is 2.50 liters. I've got T1 is 288 Kelvin. And we're going to say that's equal to V2, which is 7.50 liters divided by X. I don't know what X is. I don't know what T2 is. Now, how are we going to use this with cross multiplication? And the way we do cross multiplication is we're going to take these two numbers that are across from each other, multiply them together, and then divide by the other number over here, which is across from your X. All right, now it doesn't matter whether one's on top of the other or not. What matters is that you're multiplying these two together, dividing by that. So let's go ahead and do that. So I'm going to say 7.50 times 288, and I'm dividing by 2.50, and I get an answer of 864. And we have to subtract off 273 to get our degrees Celsius. So that is 864 minus 273, and that gives me 591 degrees Celsius as my final answer. So that's my temperature. If the new volume is 7.50 liters, so we started with our combined gas law equation. We cover up what we don't need, which in this case is the pressure, and we work with just the volumes and temperatures, make ourselves a table. And you have to, if you have degrees Celsius, and any problem that has temperature in it, it's going to be in degrees Celsius. So the first thing you got to do is you do have to turn it into Kelvin. A gas with an initial pressure of 1200 millimeters mercury at 155 degrees Celsius is cooled to minus 25 degrees Celsius. What is the final pressure? Now this problem has pairs. You got a pair of pressures and you got a pair of temperatures. So we do know we're going to need to start with the combined gas law equation so that we can get the appropriate equation that we're going to use. And so I will make myself a small table, and let's see, we'll do P1 and then T1 and P2, T2, and our initial pressure, where our initial pressure is 1200 millimeters mercury, and our beginning temperature is 155 degrees Celsius. Our final pressure, well, I don't know what that is. And the final temperature is minus 25 degrees Celsius. Now, once again, anytime we have a problem, we have to make sure that we have the correct units. Millimeters mercury is just fine, but there's a problem here with the temperature. It has degrees Celsius. So we will have to add 273 to get these into Kelvin. So this would be 428 Kelvin. And we'd have to add 273 here, and that would be 273 minus 25. Safer to use a calculator, and that's 248 Kelvin. So there's my temperatures. They are now in Kelvin. Pay attention to the minus sign there. That means subtract. So 273 minus 25 gives me 248 Kelvin. Now I can go ahead and get the equation that I'm going to need. And it looks like we only have pressures and we have temperatures, so we're not going to use the volume. We're going to cover up the volume, and this is going to be P1 over T1 equals P2 over T2. Now we can come in here and go ahead and put our numbers in, and P1 would be 1200 millimeters mercury. We have T1 as 428 Kelvin, and that's equal to the second pressure, well, we don't know what that is, and the final temperature, which is 248 Kelvin. We're going to do cross multiplication. It'll be this number times that number divided by that number. And so we're going to go ahead and put that in our calculator. 1200 times 248 divided by 428. And I get 665 millimeters mercury. 665 millimeters mercury. A gas with initial pressure of 8.05 atmospheres at 25 degrees Celsius has the pressure changed to 17.6 atmospheres. What is the new temperature in degrees Celsius? So first off, we'll need my combined gas law, because I see pairs of pressures and I see pairs of temperatures up there. And so the equation that we're going to have to use for this is going to be P1 T1 equals P2 T2, because volume is not changing, so we go over here and we just cover up the volumes, and this is the equation that we'll end up using from our combined gas law equation. Now let's go ahead and make a table, and we'll go P1 T1, and we got P2 T2, and we'll go ahead and pull in, that is in atmospheres, 8.05 ATMs. We got 25 degrees Celsius for our starting temperature. What's our new pressure? Our new pressure is 17.6 atmospheres. And our new temperature, we don't know what that is. Now, as usual, you're almost always going to, if you have a temperature, it's going to be in degrees Celsius, so we have to add 273, and that's 298 Kelvin. Now I'm ready with my units. I've got pressures are in atmospheres. I have the temperature in Kelvin. So we can go ahead and plug in to our equation. So P1 is 8.5 atmospheres. And we got 298 Kelvin for temperature 1. We have our second pressure, which is 17.6 atmospheres. And I don't know what that final temperature is. And to solve this, we're going to use cross multiplication. I'm going to multiply 17.6 times the 298 and divide by the 8.05. So I've got 7.6 times 298 divided by 8.05, and I get 652 Kelvin. Remember, your units when gas law calculations, Kelvin is going to be the units you're going to use. It's also the units that you're going to get. Now what do? I need to get it in degrees Celsius, so what I need to do is subtract 273 off of that to get the degrees Kelvin, so minus 273, and that is 379 degrees Celsius. 379 degrees Celsius.